we want to talk about what a set is. A set is simply a collection of objects. Now, what are these objects? These objects can be called both elements or members. And sets are designated using the following three methods. So we can designate a set using the word description. An example of this would be the set of even counting numbers less than 10. The second way is the listing method. Where we use these curly braces and we just list out the elements of the set. So 2, 4, 6, 8. Third way is set builder notation. Which is going to be in this format. X such that X is an even counting number less than 10, like that. So for set builder notation, this variable right here represents an element in the set. And this whole description right here is the criteria by which an element qualifies for membership in the set. Now, sets are commonly given names, and in this book, they're usually given capital letters like E. So, set E is equal to the set of even counted numbers less than 10. So, this is the name of the set. Now, a set containing no elements, so no elements, is going to be defined as the empty set. Or null set. And how do you denote an empty set? Well, we use this symbol right here. This symbol is used to denote an empty set. You could also use empty curly braces to denote an empty set, and they both have the same meaning. But what you don't do is you don't denote an empty set by doing this. Because what this represents is this set has one element, and that element is the empty set. So when we're denoting an empty set, do not use that. Now, we can do some examples. So when we want to list elements of a set, and we're given an example of the set of counting numbers between 8 and 13. So the set of counting numbers between 8 and 13 can be denoted as 9, 10, 11, 12. And it's important to note that the word between, if you see this, it excludes the endpoints. So when we're doing like quizzes or tests, it's very important to make sure we're reading properly. And if you see the word between, it excludes the endpoints. And we also run into instances where we want a set to be well-defined. What does it mean to be well-defined, and what does it mean to be not well-defined? A well-defined set is if you can always tell clearly whether something belongs to it or not. There's no ambiguity. So a well-defined set is when you can tell clearly whether something belongs to it or not. And a set is not well defined if it depends on an opinion or judgment. So for example, if we were to say that x such that x is a natural number less than 10, you can say, yeah, that's a well-defined set because you can definitively say yes or no to any number. However, when we say x is a vowel or x is a good athlete, x such that x is a good athlete, good is subjective. You can disagree with what a good athlete means. So a simple test is to simply ask yourself, could two people reasonably disagree about whether something belongs to it? If you answer yes to that, then it's not well-defined. If you answer no, then it's well-defined. Another important symbol that we need to know is whether something is an element of a set. And the way we denote that is using this right here. So if you were to do Q, we would read that as Q is an element of set E. If it's not an element, we denote it as follows. Q is not an element of set E. Then we run into sets of numbers and cardinality. And this is important to learn when taking this class of differentiating between what a natural number is, whole number, integer, rational numbers, real numbers, and irrational numbers. So natural numbers, also known as counting numbers, are going to be from 1 to infinity, right? Whole numbers are going to be from 0 to infinity, right? So the way I differentiate between natural or whole numbers, natural numbers can also be known as counting numbers, and when I'm counting something, I'm not going to count 0. So that's how I differentiate between a natural and a whole number. An integer is going to be from negative infinity to positive infinity. Irrational number is going to be as follows. P over Q such that P and Q are integers and Q cannot equal 0. Real numbers is a number that can be expressed as a decimal. So we're doing this set builder notation, x such that x is a number that can be expressed as a decimal. Irrational numbers are where x is a real number and x cannot be expressed as a quotient of integers. So square root of 2 or pi are things that cannot be expressed as a quotient of integers because decimal representations of irrational numbers are neither terminating nor repeating. Then we move on to cardinality. Cardinality is simply the number of elements within a set. And the way we denote what cardinality is n of a, which means n of a, which means how many elements are in the set. So if we have a set A, like 1, 2, 3, 4, and we want to know the cardinality of A, well, we look at how many elements are in there. There's 4 elements, so the cardinality of this is going to be 4. And then we move on to finite and infinite sets. If the cardinality of a set is a whole number, so cardinality is a whole number, it's a finite set. If it's not, then it's an infinite set. So 2 examples of this would be 1, 2, 3, 4. The cardinality is 4. It's a whole number. So this is finite. However, if we have 1, 2, 3, 4 until infinity, well, that tells us it's an infinite set. Then we look at equality of sets. So set A is equal to set B if 2 conditions are met. And so the 2 conditions are as follows. First one is every element of A is an element of B. Every element of A is an element of B. And the second condition is every element of B is an element of A. Is an element of A. And so when we're determining whether 2 sets are equal, we can look at 2 sets. For an example, so A, B, C, D, and A, C, D, B. Are these sets equal to each other? Well, they both contain A, they both contain B, they both contain C, they both contain D. So every element in this set is an element in this set, and every element in this set is an element in this set. So they're equal to each other. And we can look at another example is -4, 3, 2, 5. So A equals to that. B equals -4, 0, 3, 2, 5. Well, they both contain A, both contain 3, both contain 2, both contain 5, but B contains 0 and A does not contain 0. And what are the two conditions that need to be met for both sets to be equal? Every element of A needs to be an element of B, and every element of B needs to be an element of A. Well, the first condition is true, but the second is not, because B contains 0, but A does not, so these are not going to be equal.